Hi everyone. Today we are going to do a brief review for our um, course on the section of diffusion. Okay, so first I'm going to discuss with you about the expectations for diffusion. And here in the next two slides, I'm listing a bunch of expectations of students, what I expect you to be able to do after finishing this section on diffusion. For example, the first one is I expect you to be able to name the major categories and the mechanism for diffusion. Okay, by category, I mean, okay, there are different ways to classify diffusion. For example, we mentioned by concentration gradient, there is so-called uphill diffusion, downhill diffusion. Uphill diffusion, diffusing from low concentration to high concentration, so-called uphill. Downhill is going from high concentration to low concentration. Okay, and of course, there are different other ways to classify diffusion. There is so-called interdiffusion or self-diffusion. Interdiffusion is the situation where there is concentration gradient. Some region has concentration that is higher or lower than some surrounding regions. But self-diffusion is for the situation that when even if the material is completely homogeneous, completely uniform in its concentration. The species, microscopic species, the atoms, molecules are still not sitting still. They would move around through the random walk fashion of diffusion effect. Okay, this is kind of different ways. Of course, the diffusing species can be different things, atoms, molecules, and by mechanism, we said, okay, there's so-called interstitial diffusion when the species that are diffusing are much smaller than the surrounding atoms. And at the same time, there would be so-called substitutional diffusion. And we have also talked about for substitutional diffusion, primarily if within the crystal, it's through the so-called vacancy diffusion mechanism instead of direct exchange of position. Of course, on the surface, there may be other mechanism, but primarily within the lattice, that's so-called the vacancy mechanism. Okay, and I also expect the students to be able to give some practical examples or applications of diffusion. For example, remember that I mentioned to get silicon solar cell, the emitter, you need the diffusion process. For corrosion process to happen, there's always diffusion involved. For oxidation of metals, there's always diffusion involved. Okay, and sometimes you want to accelerate all the diffusion to happen. For example, if you have a steel part, a metal part, and you want the surface to be harder, you diffuse carbon or nitrogen into the steel part to make the surface harder. In some situations, you want to slow down or prevent the diffusion, such as the diffusion barrier layer that people put into silicon semiconductor to prevent the copper metallization layer to penetrate into the emitter or other semiconductor parts. Okay, all these are examples or applications or occurrence for diffusion phenomena. In essence, it's happening almost everywhere. It's a very broad kinetic phenomenon. Okay, I also expect the students to be able to understand the similarity and difference between uphill diffusion and the downhill diffusion. Again, both of these processes in terms of similarity, they are driven by the underlying chemical potential for the species, microscopic species, atoms, or molecules involved. Okay, the difference, of course, is from concentration point of view. Downhill is from high concentration to low concentration region, while uphill is from low concentration to high concentration. But the similarity is that they are both driven by the reduction in chemical potential. And when the chemical potential is uniform, it's the same throughout, then the microscopic diffusions appear to stop. But self-diffusion always happens. Okay? And also expect you to be able to remember the Fick's first law and the second law. The Fick's first law relates the flux, which is the flow of material per unit area per time by diffusion phenomena with respect to the so-called concentration gradient and a constant of diffusion coefficient. While the second law relates how fast does the local concentration change with respect to time with the how fast does the local concentration gradient changes. Okay, and we can simplify the Fick's second law if the diffusion coefficient is a constant, which means it doesn't change with respect to concentration. And I expect you to be able to derive these two laws based on simple one-dimensional geometry, one-dimensional. Okay. And I also expect you to be able to calculate what? The so-called activation energy, Q, and frequency factor um, in front for the diffusion coefficient if you are given the diffusion rate at different temperatures. Okay, this is very, very important. And with the activation energy and the frequency factor, you can also back calculate the diffusion coefficient at all different temperatures. We remember we mentioned diffusion coefficient is kind of a matter of how fast the diffusion would happen for a given system. For a given system. And for simple models such as interstitial diffusion in a simple crystal structure, we can have a very uh, simple understanding of where the diffusion coefficient is modeled is come from. Okay. And I also expect the students to be able to derive concentration profile for steady state diffusion one dimensional. Okay. Well, steady state, which means the diffusion flux is a constant, and under that situation, if the diffusion a coefficient is a constant, then we should have a simple linear relationship between the concentration and the distance or location. Okay? And I also expect the students to be able to name major example solutions to Fick's second law or the non-steady state diffusion equation. I do not expect you to remember the exact mathematical detail, but at least you can be able to, okay, enumerate or give examples of the typical scenario or situation for diffusion. For example, the so-called semi-infinite diffusion couple. Okay? Semi-infinite diffusion couple. When you join two uh, di different material together and they interdiffuse into each other. And another example could be, for example, the carburization, which you are driving carbon into a thick iron plate, and how does the concentration profile change with respect to time? Okay, and also there is a situation of so-called a spin undopant. You put a finite source onto the surface of the material and let it diffuse into the bulk of the material. And how does the concentration change with respect to location and time? I expect you not to remember the detailed math, but at least be able to, okay, remember the situation or scenario for these different situations and give the examples. I also expect you to remember the expression of diffusion length, which typically is given as the square root of dt, d for diffusion coefficient, t for time, square root of d times t that give us the typical diffusion length, and be able to explain its significance. It's kind of a approximation of the depth within the material that is impacted or significantly changed by the diffusion phenomena, and is a result of two factors. One is diffusion coefficient, one is time. Of course, the longer the time, the longer the diffusion length. And at the same time, the higher the diffusion coefficient, the longer the diffusion length. But it's relationship of square root of dt. Not linear, but square root of d times t. Okay? I also expect students to be able to understand the relationship between self-diffusion and the vacancy diffusion. Okay, we said within the material, the vacancy would also be able to diffuse, and the vacancy can jump to any nearby locations. While self-diffusion, in order for it to happen, not only the atom has to vibrate to attempt to jump, but also it also needs a vacancy to be nearby, um, to be in the next location in order for the self-diffusion to happen. And this links the so-called self-diffusion coefficient and the vacancy diffusion coefficient. And naturally, the vacancy diffusion coefficient would be much higher than the self-diffusion coefficient. Because in order for self-diffusion to happen, it needs a vacancy to be nearby. Okay? Then we have additional expectation about diffusion. And I expect you to understand the significance of kokondo effect. Remember we said kokondo effect is Kokondo, he observed that when he put copper and brass together, and in between them he puts the molybdenum wire in between them, and so-called inert marker. And over time, he found that the inert marker would move from the pure copper as if into the brass, indicating the interface between the brass and the pure copper moves. And the implication is that the different species would have different diffusion rate, even though they are similar, but they are not exactly the same. Copper and zinc, in that case, diffuse at somewhat different diffusion rate, and they would diffuse through the so-called vacancy mechanism, not the so-called direct exchange mechanism. That explains the movement of the kokondo marker, and I expect you to be able to understand it and explain its implications. I also expect you to be able to understand the derivation of Dawkins equation. I do not expect you to remember the derivation of Dawkins equation, but you have to be able to understand the two Dawkins equation. Okay, one is about interdiffusion coefficient d delta, and the other is about the movement movement of the interface. Okay, and the implication, and be able to use them to solve simple problems. Okay, and also remember for a given system, for example, between copper and the nickel, the system has only one interdiffusion coefficient for a specific concentration, but that interdiffusion coefficient of d delta actually changes as the system composition changes between copper and the nickel in the copper nickel system. Okay, be able to understand and use those equations. And I also expect you to understand the relationship between diffusion coefficient and mobility. Those two are closely related together, and knowing one, you can calculate the other one. Okay? And I also expect you to be able to explain the relationship between tracer diffusion, intrinsic diffusion, and the interdiffusion coefficient. Remember, interdiffusion coefficient is a single number describes the system for a given concentration, while tracer diffusion coefficient is for the radium active tracer, how fast does it move within the material. Well, intrinsic diffusion coefficient is about the diffusion coefficient that is due to pure Brownian motion. There's no concentration gradient, and all these three are related to one another. Okay? And I also expect you to be able to understand some Matano analysis. Um, and why this analysis is needed, because we said the diffusion coefficient actually may change with concentration, and for those situations quite often there's no analytical solution, which means even if we have the concentration profile, we cannot easily fit the data to get the diffusion coefficient, and then we have to do this analysis in order to solve graphically the diffusion coefficient at different concentration. Okay? And I also expect the students to be able to explain how diffusion coefficients are obtained in experiments under different situations, whether the diffusion coefficient does not change with concentration or it changes with concentration. Okay? And I also want you to explain the relationship between apparent diffusion coefficient through crystalline material with simple defects, for example, dislocations or grain boundaries. Okay? And finally, I expect students to be able to draw the concentration profile if there are reaction diffusion involved. There are different phases. Okay. These are the expectations. And when I say be able to understand, and you should be able to understand and describe it, and when I say be able to use it to calculate, then you should be able to use them to calculate. And when I say be able to derive, then of course I expect you to be able to derive. Okay?